Woohoo! Welcome back. Today we're going to be studying polynomial functions and their graphs. And I've invited Sharktopus to join us because Sharktopus has many arms, just like polynomial has many nomials, many terms. And we're going to start off with the model for a polynomial function. And you'll notice that what we've done is we've written out x to the nth, so we've got the exponent of x, and then right next to it we've got a number a sub n. And at first it can be a lot of things to take in, but the intention is to make it very straightforward. So for example, when we look at the term that has x to the first power, or just x, that number in front of it will be called a sub 1. So the subscript for the a is going to match the exponent of the x. And if that's a little bit gobbledygooky right now, that's okay. We will get to an example right now. So one example is 3x to the fourth minus x squared plus 12x minus 47. So I'm going to go ahead and write this out as 3x to the fourth plus 0x cubed minus 1x squared plus 12x to the first minus 47. And when you write it out that way, in descending order, I've got x to the fourth, x to the third, x squared, x to the first, and then our constant term. It's a lot easier to see, oh, wait, the coefficients, those are the numbers in front of the x's. For example, a sub 4 is 3. That's the coefficient of x to the fourth, the number in front of it. A sub 3, which is the coefficient of x cubed, is 0 because there isn't an x cubed term. A sub 2, the coefficient of x squared, is actually negative 1. You get to hold on to that negative if it appears right before the coefficient. A sub 1, it's moving over a little bit, but x to the first, the coefficient in front of x to the first is 12. And then a sub 0, or sometimes people call it a naught. Not like cannot, or not like not. This is sometimes referred to as NAUGHT, which means nothing. And so a sub 0, or a naught, is negative 47. That is also called the constant term. Woohoo! It's the term that is constant. It doesn't have an x attached. Now, for the degree of a polynomial is the greatest degree in the polynomial. So what are degrees? Basically, they look at the powers of x. So this term has degree 1, this term has degree 2, this term has degree 3, this piece has degree 4. The overall degree of this polynomial is 4. Woohoo! It's whatever the biggest. The biggest degree in the polynomial. And then the leading term is 3x to the fourth. Now, in this case, it happens to be first, but it isn't always just the one that's first. It's the one with the greatest degree. And the reason for this is that, in general, whatever the biggest degree is in a polynomial will determine the shape of the graph. It'll determine the behavior. We're going to talk later something called end behavior. That will be determined by that leading term. So the leading term is the one that we need to look to decide what the big things are going on with that polynomial. The other terms kind of add spice to the polynomial. So it's like the leading term tells you that you're making, say, a chicken dinner, and then all of the other terms determine, are you gonna add paprika? Are you gonna add garlic? This is all the spices to make this polynomial look a little bit different. But the leading term is going to be that basic idea. Are you making tofu surprise? And are you going to put scallions in, or are you going to put soy sauce in? You know, what do you want to do to spice it up? So that's their basic introduction to polynomials. We're going to move on in this chapter and in the homework into something we've done before, which is setting up a basic library of the shapes of functions so that you could look at y equals x or y equals x cubed, y equals x to the fifth. These are all the odd functions. Well, not all of them, but these are all odd functions, or even functions like y equals x squared, y equals x to the fourth. And once you have an idea of what these graphs look like, then we're going to use transformations just like back in the last chapter. So let's take a look. I actually went ahead and prepared this. Ooh, so fancy. We've got the graphs of these functions already typed up in Desmos. And so let's take a look at which is which. First off, Desmos does not add x and y and arrows, so we of course have to add that ourselves. If you can see the colors on the screen, this straight line is y equals x, which technically qualifies, although most of the polynomials that you're going to encounter will be at least degree 2, so like x squared, x cubed, x to the fourth, but lines still qualify. They're just slightly less curvy, right, because they're generally straight lines. How can we see that this is an odd function? Well, we can see that it's got this shape where when x is positive, y is positive, and when x is negative, y is negative. So as you change the sign of x, y flips around 180 degrees. And we talked before about that pinwheel, that an odd function, if you put your finger on the origin and you turn the whole thing around 180 degrees, you get that mirroring. So if it comes up here or if it goes down here. Things are still odd if they go in the other direction. So for example, I could also look at a graph. I'll make this one dotted so you can distinguish it. If I had y equals the opposite of x, that's still odd. When x is negative, y is positive. When x is positive, y is negative. So there's that 180 degrees, except this flip, we can, the symmetry we can see going in slightly a different direction. It's still going around the origin, but we're going from the second quadrant to the fourth. Okay, so now we've got these other two graphs here, and hopefully you can distinguish them. There's one that's slightly green, and it may be hard to see. So since it may be hard to see, I'm going to emphasize it with a little bit of highlighter. And you'll see that the two graphs switch places. So in other words, they intersect here. In fact, all of these graphs intersect there. And then they also intersect here. And this point is the point 0, 0. This is the point 1, 1. And this is the point negative 1, negative 1. But you'll see that this other graph dips underneath here, but then surges ahead. And here dips above and then surges below. So they're swapping places. There isn't one that's always on top and one that's always on the bottom. And so our job is to figure out which one is x cubed and which one is x to the fifth. And the answer is that this one, which is the one I just highlighted, if you can see that color in green, is x cubed. And this one that's slightly above it, past 1, 1, is y equals x to the fifth. Now, y is x to the fifth above and x cubed is below, but then they swap places. So let's look at a table of values. Let's look at y equals x, and then x cubed, and then x to the fifth. So if x is 0, x cubed is 0, and x to the fifth is 0. easy peasy. If x is 1, x cubed is 1, x to the 5th is 1, easy peasy. So we can see these overlap points. But what happens when x is 1/2? So x cubed, and now I regret not giving myself more space, is 1/2 cubed, which is 1/8. And x to the 5th is 1/2 to the 5th, which is 1/32. You can double check that on a calculator. So in fact, x cubed, when x is 1/2, so right here, x cubed is above x to the 5th. Because when you cube a fraction, it's bigger than when you take it to the 5th power. So if something is smaller than 1, and you raise it, well, between 0 and 1, I should say properly, and you raise it and you cube it, you're going to end up with a bigger number than if you take it to the 5th power. On the other hand, if we look at a number like 2, 2 cubed is going to be 8, and 2 to the 5th is going to be 32. So in terms of 2, and you can't even see it on this graph because the numbers get so big, but x cubed is less than x to the 5th. So right here, x cubed is greater than x to the 5th, and right here, x cubed is less than x to the 5th, right there and right there. And so we get them flip-flopping like that. And we see it happens again, it mirrors it when x is negative. So that's what x cubed, x to the 5th. And so you could think, what would x to the 7th look like? And x to the 7th would look just like this, but it would dip down below x to the 5th and then swap places and then surge ahead. Okay, let's take a look at these two. Now these two are, again, I haven't drawn in the arrows or anything because Desmos doesn't give us those. But basically, I've got x squared and x to the 4th. And we see, again, they match up at the point 1, 1 at the origin and at the point -1, -1, +1. Hello. And these are even functions because whether x is negative or positive, y is the same. So they scoop around and you get that butterfly. You get the symmetry about the y-axis. Remember, you draw it on one side and then you close it up and you open it up and you've got that beautiful butterfly on both sides. So the question becomes, which of these is x squared and which one is x to the 4th? And we see that one sinks down below but then surges ahead. And from what we did up here, hopefully you say, oh, yeah, that would be x to the 4th. And this one would be x squared, because x squared is going to be slightly larger between 0 and 1, but then x to the 4th is going to get much bigger, much faster. And the same thing over here. This is x to the 4th, and this is x squared. So what I would encourage you to do, whether or not this made a lot of sense or whether it made no sense whatsoever, go into Desmos or another graphing utility and make sure you know what the graphs of all of these functions look like. Play around. Try x to the 16th. Try x to the 13th. And look at the graphs and compare them and feel really comfortable with it. Okay, so woohoo, let's move on. So the next thing we're going to talk about, if I can get to the next page, which it seems I cannot, is going to be some terminology that I just wanted to go over. It's something that's going to come back when you get to calculus. And so I wanted to introduce the concept. So when you get to calculus, you'll be like, oh yeah, I remember these things. So the book asserts, and I will assert, that the reason that we're studying polynomials is that their graphs are really nice. The graphs of polynomials are smooth and continuous. So smooth means it's not jaggedy. It doesn't suddenly surge up and surge down. It moves in a smooth curve. Continuous means that there are not any sudden jumps or breaks. So we actually in math have names for these various things. So the book says without breaks, holes, corners, or cusps. And I wanted to show you what that looks like. So a break means that something stops and then suddenly jumps up. That's a break. Now, this could also be considered a break, but a lot of times people refer to it as a hole. And that's just that there's a point that's just completely missing. Who knows where it went? And so a break like that or a hole like that make math really difficult because there's this sudden change, and that's going to be hard to look at. The missing point here means that it's going to be really hard to do math around that point. So again, polynomials don't have these, so it's really nice. Now, cusps and corners, they seem really, they've always seemed very close to me, but basically a cusp is a pointy thing, like it comes up and it on both sides. And what that means is the concavity is the same on both sides. Now, I'm using a word that we haven't used a lot, so it's hard to really be rigorous about this definition, but basically it looks like a little point, either pointing up or pointing down. That could also be a cusp. A corner is going to be something where the graph is coming up and then suddenly it changes. Now, again, this corner and this cusp look really close. So what I'm going to do is I'm just going to say they're very similar. And when you get back up to calculus, we'll talk about it a little bit more. But basically, the idea is we don't have those. So you don't have to worry about it for right now. Smooth and continuous means that it's just a really nice, gentle, round curve like this. It's going to make it really easy to study. And also easy to graph, because if I tell you there's a point here, and I tell you there's a point here, and I tell you there's a point here, if there could be corners or cusps, it's going to be hard to know, or even breaks or holes, like how do I know where it goes? And the answer is that if you just plot a few other points, generally speaking, you can play connect the dots and be pretty certain that, you know, plus or minus, you've got the basic shape. So that's what's going to be nice about it. Now, is it possible that if I plotted another point, it turns out that it goes down like this? Yes. So the answer is going to be sometimes you're going to want to be very careful by choosing a lot of points to plot, but still, smooth and continuous means it won't be doing anything completely surprising like these. Okay, woohoo! Last thing I want to talk about in this video is the end behavior of the polynomials. Woohoo! Oh, and I should point out, Sharktopus, look at these smooth continuous arms. Woohoo! Nicely done, Sharktopus. Thank you so much. Okay, so unfortunately, Sharktopus still has that hat on. That's some cuspy stuff up there, but that's Sharktopus's hat, so we don't have to worry about it. We just take the hat off, I'm sure. So the end behavior of polynomials. The end behavior of a function refers to what happens when x gets really big, really positive. So x gets large without bound is how we say it. X approaches infinity is how you could say it sometimes. Infinity can be problematic with language. So generally we just say x gets really, really large because infinity isn't a number in math. It's a concept. So, and then also what happens when x gets really negative? So now here's the problem with the English language. We would like to say it gets really, x gets really large, means x gets really big, and x gets really small. But the problem is sometimes small means like fractional, and sometimes small means really negative, but a large negative number. And so it is imprecise in math. So we generally can then say it gets really negative or x decreases without bound. And again, these are things that are going to come back in calculus. So I'm kind of just planting little seeds for what's going to happen next. And what we want to look at is the end behavior of polynomials. Now, how is that going to help us? Well, if we know what happens when x gets really big or when x gets really negative, then for our graph, we'll go back to this one we were looking at before. Do we know for sure that this just heads down forever, or does it maybe take a U-turn and go back up? That would be important to know. Same thing over here. Does this keep going up, or at some point does it come back down and end up trending down? So that's what we're looking for, is what happens on the far sides of the graph. So the end behavior of the polynomial. And again, when x gets really, really large, three x to the fifth is much bigger than the rest of the polynomial. What do I mean by that? Well, if you imagine if x is 10, 10 to the fifth is a 1 with 5 zeros, right? So that's going to be 100,000. So this is going to be 300,000. The next term will be minus, and then x cubed, 10 cubed is like, what is that? That's 1,000. So this is going to be 300,000 minus 5,000. So if I say, I'm going to give you 300,000, but I'm going to take away 5,000, you're going to be like, okay, that's still basically 300,000. So the leading term becomes the most important term. So we look at 3x to the fifth. When x gets really, really positive, 3x to the fifth gets really, really positive. So in other words, it's going to go up at the end. And when x gets really, really negative, 3x to the fifth, now we got to think about it. When x is negative, x to the fifth is even or odd? And the answer is it's odd. It means that the negative just passes right through. And so x to the fifth, if x is negative, x to the fifth is also negative. So this is going to go, well, I don't want to draw it like that. Sorry about that. What? Look over there. There's something behind you. Oh, look, it's a rainbow or a shooting star. So when x gets very negative, so we're heading, I made it go in the wrong direction. It goes down like this. So what does this graph look like? In other words, it does that, and then there's something mysterious in the middle, and then it goes up. That's what the graph is going to look like. Next up, determine the end behavior of this polynomial. So now I've got p of x equals negative 3x to the fifth times the quantity 2x minus 1. Now, if I have it written like this, that means that I want to possibly obscure something, right? This is written in a funny way. This is not the way that we expect polynomials to be written. Polynomials, generally speaking, should be written out like this: term plus term plus term plus term. This is written out kind of goofy. So our first step should be to actually look at what's going on. I've got negative 3x to the fifth times these two terms, so let's go ahead and multiply them out. Negative 3x to the fifth times 2x is negative 6x to the sixth. Negative 3x to the fifth minus 1 is plus 3x to the fifth. And again, we look at the leading term. We look at the negative 6x to the sixth. When x gets really positive, x to the sixth is really positive times a negative 6. That means this is going to go down at the end. So negative 6x to the sixth gets very negative. When x gets very negative, well, x to the sixth is even, so it doesn't matter whether x is positive or negative. The end result is going to be positive, right? Negative 1 to the sixth power is going to be positive 1. So it doesn't matter what x gives you, what x is, it's going to come out being negative. So we've got one of these. So this polynomial is going to look like this. It's going to, as x gets very, very negative, it's going to go down. Then there's something in the middle. We'll worry about that later. And then when x gets really, really big, it's going to end up looking like that. Okay. So, in general, what is the end behavior of an odd function? We got two possibilities. In general, an odd function is going to look like this, or it's going to look like this. An even function, and again, I'm not writing the middle stuff because we don't know what the middle stuff looks like. Either it's going to go up on both ends, or it's going to go down on both ends. And so I know you're probably looking at all this going, how are we even going to use this? And the answer is, in the next couple of videos, we're going to build on this, and we're going to get to the point where we can actually graph a polynomial, and we will use this to decide how the graph goes. So let me grab that graph page that we have. So for example, these three functions all go up. So as x gets very positive, y gets very positive. So they go up that way. This is the question mark in the middle that we wouldn't necessarily know. And then when x gets really negative, y goes down. So that would be this example right there. Would look like this. And then this line is this example. It's up on the left and down on the right. Okay, for even functions, oops, don't fall down. We're almost done. Courage, we can do it. For even function, either both ends go up or both ends go down. And you can see these two examples, both ends go up on the left, up on the right. And so that's going to help us determine what the graph looks like. Okay, you guys are awesome. That was a long video, but you made it. Thanks to Sharktopus and his very smooth and continuous arms. And thanks to you for being brilliant. And so, you know, take a break. Go look at something green. Get outside if you can. You know, move your body. Get a snack. Get some hydration. And then come on back because we're going to continue with our second video in this section. You guys are awesome. See you then. Woohoo. Math on.